Hello everyone, and welcome to this explainer prepared for the 34th International Materials Research Congress. Today, we are unpacking a comprehensive theoretical study on one-dimensional strontium-zirconium oxide, or SrZrO3, nanowires. We're going to explore how altering their structure at the absolute atomic level fundamentally dictates their electronic behavior, and really why that matters so much for the future of technology.
So you might be wondering, why focus on one-dimensional systems in the first place? Well, taking a bulk material and reducing its dimensions right down to the nanoscale offers us just an incredible degree of control. By tuning these materials structurally, we can literally pave the way for highly advanced, next-generation nanoscale electronic and optoelectronic devices. It's a true macro-to-quantum journey.
Here is our quick roadmap for today. We'll introduce the core objectives, detail our computational methodology, explore the properties of specific nanowire orientations, and finally, wrap up with the broader implications.
All right, starting with Part 1, Introduction and Objectives. Our main goal here was to isolate exactly how two specific variables influence the overall properties of SrZrO3. Those variables being the crystallographic growth direction and the structural size of the formation unit. The push to study complex systems like these nanowires is really driven by a massive demand for superior optoelectronic properties. Isolating a material to the nanoscale completely modifies how it behaves. It gives us this totally unique opportunity to engineer better devices directly at the atomic level.
Moving right along to Section 2, let's look at the computational methodology that builds the rigorous foundation for this theoretical work.
To guarantee high precision, our structural optimizations and electronic calculations relied on density functional theory within the siesta code. We utilized the generalized gradient approximation with a GGA-PBE functional to properly model those electronic interactions. And for ultimate accuracy, we achieved total energy minimization using a precise optimized mesh cutoff of 120 Rydbergs, alongside a K-point grid of 1 by 1 by 7, intentionally orienting those 7 points directly along the nanowire's growth axis.
That brings us to Section 3, Structural Properties and Variations. Following that geometric optimization, we first needed to analyze the resulting equilibrium lattice parameters.
Notice the atomic arrangements here with strontium, zirconium, and oxygen interacting. We modeled 3 distinct formation unit sizes, the 2x2, 3x3, and 4x4 units. And we did this across 2 very distinct growth directions, the 100 direction and the 110 direction. From those optimized structures, we extracted the precise lattice parameters. And you know, the data tells a fascinating story of spatial expansion. For nanowires oriented along the 100 direction, the lattice parameters are 4.035, 4.130, and 4.161 angstroms for the 2x2, 3x3, and 4x4 sizes, respectively. You see a steady, predictable increase. But wow, look at the 110 direction. It results in significantly wider parameters of 5.818, 5.869, and 6.008 angstroms for those same formation units. This proves absolutely that crystallographic orientation heavily dictates structural dimensions.
Now into Section 4, Electronic Properties and Band Gaps. The absolutely crucial question here is, how do these distinct structural expansions directly influence the semiconducting nature and the energy barriers of our nanowires?
Well, our calculations confirmed clear semiconducting behavior. Looking at the band structure for the 100 systems, we observed exact band gap values of 2.268 electron volts for the 2x2 size, 2.096 electron volts for the 3x3 size, and 2.273 electron volts for the larger 4x4 unit. So, pretty stable overall.
In sharp contrast, the 110 direction tells a dramatically different story. This orientation yields significantly reduced band gaps. We're talking exactly 1.624 electron volts for the 2x2 system and just 1.059 electron volts for the 3x3 system. While a 4x4 band gap was not modeled for this specific orientation, that steep downward trend in the energy barrier compared to the 100 direction is incredibly striking.
Let's move to Section 5 and compare these two structural behaviors directly to understand the broader tunability of these nanowires. When we put the data side by side, the divergence is clear as day. The 100 orientation maintains a relatively stable higher bandgap range, sitting between approximately 2.1 and 2.3 electron volts, regardless of the formation unit size. However, the 110 systems exhibit a massive reduction in the energy barrier, dropping down to 1.624 and 1.059 electron volts. This highlights a real game changer. Simply changing the direction of crystal growth completely alters how electrons behave within the exact same material.
Finally, bringing us to Section 6, Conclusions and Future Applications. It's time to anchor these theoretical findings in their real-world potential.
Ultimately, this first principle study proves a vital concept. The electronic properties of one-dimensional SrZrO3 nanowires are not fixed. They can be directly and precisely tuned just by controlling structural size and crystallographic orientation. Because we can effectively dial these bandgaps up or down, these nanowires stand out as highly promising candidates for future nanoscale electronic and optoelectronic devices. It leaves us with a truly exciting thought. If we can literally program a material's electronic behavior just by changing how it grows at the atomic level, what limits are even left for the next generation of optoelectronics? Thank you for your attention.